All right, guys, welcome back to another lesson. Um, Today's objective is we're going to talk about scatter plots and lines of regression. So stuff that looks like this. And if you notice from the picture, there isn't a line that will connect all those dots. Okay, this is using real world data. So what we try to do is we come up with a line that roughly tells us the behavior of things. Okay, and that's going to help us make some future predictions. Maybe not the most accurate at times, but it gives us an idea. Okay, so the scatter plot is just all this data graphed, and then that line of regression or line of best fit, whatever you want to call it for right now, is what we're going to try and calculate here. Okay, PowerPoint slides. I do have them printed for you or uploaded, so feel free to print those out so you can kind of follow along because there's a lot of writing here and it makes it a lot easier if you have these ahead of time. So we wrote linear equations. Now we're going to use scatter plots and prediction equations, and we're going to model some data using lines of regression. A lot of vocab here. So some of it you might have heard before, positive, negative correlation, okay, correlation coefficient. You've seen scatter plots before, dot plots, kind of like the same thing there. Bivariate data regression line might be a little bit new for you. Line of fit, prediction equation, those things we'll talk about, okay? So bivariate data is just data with two variables. That's all it is. Okay, usually what we have x and y. Okay, those are two variables in question. A scatter or dot plot is just using this bivariate data to be graphed in a coordinate plane. Okay, and usually we stick in quadrant one, right? We have all the positive y values and positive x values that we're going to use. Okay, sometimes we'll show a little bit of quadrant two just to see, where it's still coming from, like past the y-intercept. So sometimes we'll do that. Just depends. So here's the type of scatter plots we could have. Now, this is the correlations that we're going to talk about. And just real quick, so we're on the same page here. Correlations are just a way to describe the graph. It's an adjective. Okay. So this graph would have a positive correlation because if I drew a line that would go through a majority, or at least is around most of the points, it has a positive slope. So positive correlation, okay? Negative correlation is the opposite. Okay, you can see all my data points are just kind of going in a decreasing motion. My line is also showing it, my line of best fit, which we'll talk about. And no correlation is, well, there isn't a line to be drawn that would contain the behavior of that data. There isn't one. No obvious pattern, no increase or decrease. So that would be a no correlation graph. Okay, and once again, all three of these are just describing what the data looks like. Okay, let's real quick, because I forgot, I don't have this in the note part, but when you hear the word line of best fit or line of fit, okay, when you see that phrase, okay, what that means is a line that closely approximates the set of data. Okay? It's not perfect. There isn't going to be a line that connects all of them because it wouldn't be a line. But it gets as close as we can. Okay? So we can also call this a prediction equation. I got to remember to add this to my PowerPoint next time. I just realized I didn't have it in there. Okay, so line of best fit it just closely approximates all the data where it currently lies. Sometimes it's called a prediction equation because we can use that to find future values. Okay, so that's what these guys are, prediction equations, line of best fit. So let's look at an example here. So here's an education example. Table below shows the approximate percent of students who sent applications to 2 colleges in various years since 1985. Make a scatter plot of the data, draw a line of best fit, describe the correlation. Okay, so here we have years. That would be your independent variable on the x-axis. Here's the percent for each year. And when you see years since 1985, just be careful. This isn't 0 years. It's just, well, this represents 1985. 3 years then would be 1988. Okay, see how we're just adding those? So instead of writing actual dates, they said years since then. Okay, so just be careful when reading that data. So make a scatter plot. Now on the PowerPoint slides, I do have a blank grid for you to graph those, but I already have it here for us so you can see. All right. So here's the percent. Here's the years since 1985. We start out pretty high at 20%, right? And then gradually, as years progress, the applications have decreased. Okay, so far to 13%. This is what, 15 years since 1985. So that'd be what, the year 2000 that we're at. Okay. Now, this would be a negative correlation. So you want to write that down because it asks you. So this would be a negative correlation. I can't spell. There we go. Now, line of best fit. This is where you're going to use your best judgment here, okay? The 2 points I used was 318 and then 1513. When I drew the line between them, it seems like, for the most part, most of the points are around those two. I could have used 20, 0, 20, and 12, 14, and drew another line, okay? So you got to use your best judgment when using these. There is one I wouldn't use right here, okay? This point, 15? Yeah, 615, okay? That would be probably considered an outlier, okay? And that just means it's kind of an odd data point. And that happens, right? When we're collecting a bunch of data, you're going to have some odd points coming out. So this one probably will not be used for future calculations, but we still represent it. That's still part of our data set, okay? So there's my answer for that guy. So far, so good. Just graphing. Part B, find a prediction equation, and what do the slope and y-intercept indicate? So here's what we're going to do, okay? We came up with a line that we think works. Okay, we think that works. It looks like it matches the data as good as it can be. Let's come up with an equation for that line. Okay? So once again, all right, the 2 points that I used, 318, 15, 13. That's what I used to create my line. So let's put this in y equals mx plus b, right? That's what we want. So a lot of ways of doing this. First, I need a slope, right? So let's find the slope. So 13 minus 18, I'll put in the top, changing my y's. 15 minus 3, changing x's on the bottom. So negative 6 over 12, or negative a half. Okay, so we got a slope. Now we need a y-intercept. A couple ways of doing this. How about, they kind of give it to us already, I think. Or no, they don't, huh? Do they give this to us? It looks like, oh, sorry. Sorry about that. This point is on the y-axis. But did we use that point to create our line? No. So I can't use 0, 20 as my y-intercept. So just be careful with that. Okay, so given the line that I have to figure out what the new y-intercept is. It's going to get close to 20. So I'm going to use point slope form. Okay, so I'm going to use, well, it doesn't really matter in this case. I think in the notes I used 318. Yeah, I used 318. Okay, 3 is a smaller number, so it's nice to work with. We got my slope, so I'm going to plug these into here. So I leave y alone. Y sub 1 would be 18. The m value is, or the slope value is negative a half. I don't change that x. And the other guy would be minus, oh, not 18. Sorry, be 3. Now we simplify. So y minus 18 equals negative a half x. This would be plus 3 halves. All right. Last step, get y by itself, add 18 to both sides. So y is negative a half x. Now over here, I could leave it as a fraction, but since I'm graphing and I want the actual data point to approximate things, I'm going to leave it as a decimal then. Okay, I think that would be for the best. So what would that be? 19 and a quarter? Something like that. my gosh. Do you see it? Were you screaming the whole time when I was solving this? You see my error? You see what I did wrong with the slope? It's up here. 13 minus 18, negative 5. Oh no. You're probably going to hate me. Hey, this is recorded live. Mistakes can happen. So let me change this. I'm so sorry, guys. It happens. So this would be what? Negative 5 over 12. That's my slope. No wonder. I'm looking at this and like, that's not 19.25 because 3 divided by 2 is 1.5. Like, wait a minute. So over here would be 15 over 12. Then add the 15 to the other side. Okay, that looks a lot better. So 19 and a quarter for that guy. So then we'll change this guy to negative 5 over 12. Perfect. I apologize, I really do, okay? Wasn't meant to happen. I went a little too quick on that subtraction, okay? So, if I look back at the graph, I can see that, all right, this equation that I came up with is what this line is, okay? So what does the slope and what does the y-intercept mean? That's the next thing we're going to talk about, okay? Well, if we take a look, my slope indicates the decrease in applications, right? Years since 1985. So years since 1985. Okay, that's the amount it's decreasing since that date and time. Up here is, well, what we start with. Okay, the percent that we're looking at here. So what? Roughly 1985, it was 19%, roughly. In 1985 was the amount of applications that were submitted, roughly 19%. Now, look back at the original problem. The original problem was what, 0.20? They said it's at 1985, it was 20%. Does my prediction equation match that? No, but it came close, right? Because once again, I'm trying to find a line that best fits all of the data, not just one point. Okay, so there's a difference there, and you want to be careful with that. So honestly, our prediction equation is not off by much. Okay, 19%, 20, okay, 1% difference, that's not too bad. Now, if your prediction equation was off by, let's say, 5 or 6%, then yeah, you might want to go back and choose 2 different points to create your line of best fit. Does that make sense? Okay, so you just want to be careful with that. All right. So, part C, but still, third part, second part, whatever you want to call it. Predict the percent of students who will send applications in 2010. Okay, so I'm now going to use my equation that I created to predict this result. Okay, just to get an estimate, so I know in the future what I would expect. All right, so looking at this, 2010. Well, let's think about it. In 2010, how many years has that been since 1985? Maybe, what, 25 years? Okay. So we're looking for, in 25 years since then, what's my output going to be? So negative 5 over 12, okay, times 25 plus 19.25. Okay, that's what we're going to try and plug into here. So when we do that, we get roughly 8.83% for that guy. Okay, so in 2010, we should expect 8.83% submission for applications. And it seems reasonable, right? If you think about it, we start at roughly 20%, and we know that the slope's negative. So 8.83% after 25 years, that sounds about right, because this is about what? About 0.4 or 4%, I'm sorry, 4% decrease each time. Okay, 0.4% decrease each time. So that sounds about roughly right. In 25 years, you get to that point. Okay, so it's pretty cool actually that we can predict something like this. Is it going to be accurate? Well, it just depends on what happens. Okay, but it's what we have. So how accurate is the prediction? We'll say it is fairly accurate. In terms of outliers, well, we do have one, right? So you could say we have one outlier. That is not an O. That's a weird-looking O. We have one outlier, and that was what, 615? Was it 615? Let's go back real quick. Yep, 615. That point right there. That was our outlier. Okay? But other than that, I'd say this is pretty good. All right? Okay, safety. The table shows the approximate percent of drivers who wear seatbelts in various years since 1994. So once again, looking at the graph, 0 represents the year 1994, 3 represents 1997, 2000, and so forth. Okay? So which one of these shows the best line of fit for the data? Okay, that's what we're looking for. Now, take a look at the table. You see how the percent is increasing? So if that's the case, then my line should be a positive slope. B and D are not showing that. So we can eliminate those two options. So really, the only option I have left is what, A and C options? So looking at A and C, you got to look to see, well, which one is the best line? And I think it's going to be C, right? C's our answer. You see how for A, they only used one, they didn't even use that point. They just drew some random line there. This is a lot more accurate because it's using 2 points to draw the line, and most of the points are surrounding it. So this one has a better line of best fit. So C would be our answer for that guy. All right. So the table and scatter plot shows the approximate percent of drivers who wear seatbelts in various years since 1994. What is a good prediction equation for this data? Use these points to figure it out. Okay, and that's the points in part C that we're looking at. So let's do that. All right, let's come up with a prediction equation for that data. We're going to use those 2 points, and I'm going to do the same thing, except this time, I'm going to find the slope correctly. All right, so 6, 71, 12, 81. Okay, so let's figure this out. So the slope would be 81 minus 71 over 12 minus 6. So that's 10 over 6, right? Which does reduce down to what, 5/3? Now I'm going to use a point. I'm going to use 6 and 71. I mean, you could use 12 and 81, but I would say 6 and 71 would be better just because the numbers are a little bit lower. So 6 and 71. That's the point I'm going to use. So I don't change the first one. The second one would be 71. My slope's 5/3, and I know it's 5/3 this time. I did the subtraction correctly. X is here. X sub 1 is minus 6. Just like that. Simplify. So it would be 5/3 X. And then this guy would go minus 30 over 3, which, hey, wait a minute. Isn't that 10? Did I get a nice number this time? Not a fraction, not a decimal to worry about? That's pretty cool. Okay, last step, add 71 to the other side. So 5/3 X. And this would be, what, plus 71, so it would be plus 61. There's my prediction equation. So that's going to be what? This option over here, which would be C, because it kind of got staggered there. So option C. Okay. D looks very similar, but it has a negative slope line, and we know from the data that it's been increasing since 1994, so it shouldn't be negative. Okay. All right. Doing pretty good so far. Let's keep going. Using this prediction equation, predict the percent of drivers who are wearing seatbelts in 2010. So we're going to use our own equation to figure this out, okay, and see what percent we get for this guy. All right, let's try it out then. So 2010, 1994 to 2010, I think that's what, 16 years? So it's 16 years. So y equals 5/3 times 16 plus 61. Okay. And I don't know, I probably should put roughly, because it's exact here, but technically it's roughly, or because this is a prediction equation, it's not exact, but if you want to, you can say that, I guess. So we should get 87%. And I guess it is kind of roughly, since this is a fraction that we're dealing with. So, and that would be what? Option B. 87%. 2010 should be drivers who are wearing seatbelts. And that's if the trend continues, guys. I mean, stuff can happen in the world, and I'm speaking in the past here. I'm speaking, that we haven't reached 2010 yet. So maybe a little outdated, but I'm just saying something could happen to where things change, different laws, and that can change my data too, right? And it has because, well, there is a mandate law to wear your seatbelt when you're driving. So something to think about there, that other things could affect the data, can affect my prediction equation, and so forth. Okay? All right. So how accurate is this prediction? Well, if you look at your options, I'm thinking option B. Okay? It's good. This is a great prediction except for one outlier in the data. Let me go back to the graph, or let me go back to the data points. Okay? Do you think there's an outlier here? I think there's one. Do you see it? It's not by much. The spacing between this and the line is very tiny. The spacing between here is a little bit more noticeable. So you could say that this guy, 9 and 79, could be an outlier. So 9, 79 would be our outlier. Not by much, to be honest with you. But other than that, I think the prediction equation did a good job. Okay? All right. Kind of wrapping things up here. So a little bit of vocab, and then I am going to have a separate video showing you how to calculate a regression line using the graphing calculator. Okay? The R value, correlation coefficient. So stay tuned for that. But for right now, a regression line is determined through complex calculations to ensure that the distance of all data points to the line of fit are a minimum. So if we were to actually create a true line without picking 2 points, but we're trying to create a line where the distance between each of these points to the line is at its minimum. Okay, that's what we're trying to create here. Now that's more for a stats course. For Algebra 2, we just need to know some of the basics. But to figure out stuff like that, okay, and actually, wait a minute, a little bit ahead. There is some complex calculation involved, but the other thing is too, we can describe if this line's good or not by what's called the correlation coefficient. It shows how well the data are modeled by the linear equation. Okay, so is this a good correlation or not? So if you're interested, here's the formula for that correlation coefficient of how to calculate it. Okay, Carl Pearson, there's his birth date and his time of death, but he's the one that came up with this guy. And this is a summation symbol, so you would add up all these values that you would be multiplying together. The x bar and the y bar are the averages of the data for x and y's. The s's stand for standard deviation. How far are you away from the mean of the data? And the x sub I and y sub I, should be sub I there. Those guys are just the individual data points you would subtract the mean from. So for individually x and y. So it's a little bit of some calculation involved, but this value will tell you whether or not your line's accurate. Okay? Now we're not going to do that in this class. Like I said, statistics you would. Not a bad calculation, it really isn't. But it's pretty cool that you can say with certainty if your line's good. So how can we use that to help us? Well, When your R value is close to -1, it has a negative correlation. Okay, so that means most of your data points are close to that line you created, okay, and it's negatively sloped. When R is 0, the data has no correlation, meaning you can't draw a line through those data points that accurately represents that data. It's not going to work. And then for the last one, R is close to 1. That means the data has a positive correlation, so that means most of my data is closer together, okay? And that means it's going in the positive direction there. All right? So just to, goodbye. Goodbye, you're gone. Okay, so for instance, if most of my points are close together like this, okay, and I draw my line, then let's say my R value is 0.97, close to 1. That's very strong, right? That's a strong positive correlation. Now, reverse of this would be this. Okay, it's still a positive correlation, right? It's still going in the positive direction if I drew a line, okay? But my R value might be what, 0.6? So it's kind of like a weak positive correlation, right? Still positive, but it's weak. Now, same thing with negative. If I went like this, okay, that is a strong negative correlation. So R could be negative, 0.98, let's say. Boy, that's a wrong place to put a negative. I'm sorry. There we go. Okay, so it's very close to -1. But if it's more sparse, it's still, see how it's still going in that negative direction, but the distance between the data point and the line is bigger. So my R value might be like -0.5. So it's kind of like a weak negative correlation. Okay, so it's just a lot of different adjectives and values to represent what the data is. And we'll talk about how to calculate this using a calculator, graphing calculator. We'll do that in a separate video. Okay, and that's it, guys. Okay, that's the lesson for data, for, line regression and scatter plots. Okay, so some of it probably review from Algebra 1. I think Algebra 1 you talked about correlations like this. In this class, we're doing the same thing, except now we're adding a little bit more adjectives involved, and we're coming up with prediction equations, okay, and we're testing them out. All right, so that's it. If you have any questions, let me know. Other than that, guys, have a good day. All right, enjoy it. I'll see you in the next video.